In this video, we're going to find the length of all sides of the figure and in the process prove the double angle identities. So we start with a right triangle and we'll just reflect that right triangle so that we can take a look at the double angle identities. So it's theta on the top and theta on the bottom, and the hypotenuse is 5. And the value for theta itself is 36.86699 degrees. And as we work on this figure, the first thing we're going to do is simplify it by scaling it back. So instead of using a hypotenuse of 5, which we will add back in later, we'll just say that the hypotenuse is 1. And instead of worrying about what the value for theta is, we'll simply say that there is an angle theta. And it's repeated as you see there at the top and the bottom. So the modification that we'll make to the figure, so in fact there will be 13 sides, is we will add an additional perpendicular. We'll start at the upper right hand corner of the upper triangle and then draw a diagonal down so that it's perpendicular with the hypotenuse of the triangle on the bottom. And this will create a figure with a total of 13 sides. So let's just name those so that they are easier to talk about. The sides on the outside will be 1, 2, and 3. And the side named 2 is actually composed of 2 different sides. So we'll call those 2A and 2B. And then 3 is similarly split up into 3A and 3B. We'll call the diagonal 4 and split it up into 4A and 4B. And we'll call the horizontal 5 split up into 5A and 5B. So that's a total of 13 sides. And what we want to do is find the length of each of those. So the first two are pretty easy. They are the hypotenuses of the two triangles. So we already know that the first one is 1. And the reflected hypotenuse, of course, is also 1. So side 1 is equal to 1, and side 3 is also equal to 1. Since we notice that this angle is theta, then the other angle in this right triangle must be 90 minus theta. And therefore, since there's another right triangle associated with these angles, we see that this angle is theta. And so that will help us to use the trigonometric functions knowing that. So using that information, we can determine the values of some of the other sides, and we'll start by noting that this value is sine theta, and so of course the reflected value on the bottom is also sine theta. So 2a is sine theta, 2b is sine theta, therefore side 2 must be 2 sine theta. And in a similar way, the horizontal line is cosine theta, and we'll also note here that we can see that the side 3a must be in fact the same as cosine of 2 theta, and the side 4 must be the same as sine of 2 theta. And of course we want to get our measurements in terms of theta, not 2 theta, so we're just noting that this is the case so that when we find the values we can create our trigonometric identity. Alright, so now that we know that, we can go ahead and break down some of the other sides based on the triangles that they're in. So we start in the upper right hand corner. Now we already know that this value is sine theta. The hypotenuse of that triangle must be sine theta divided by cosine, because you can see that that's its relationship to the angle theta. And of course sine divided by cosine is tangent. So 4a is tangent theta. And then using the value of that hypotenuse, knowing that the angle at the top is theta, we know that all you have to do is multiply tangent theta by sine theta, and that will get you side 5b. So that's 4a and 5b. And now we've got enough information to determine some other sides. So we already know that 5 is equal to cos theta, and 5b is sine theta times tangent theta. So that must mean that 5a is simply a subtraction of 5 and 5b, so that would be cos theta minus sine theta times tangent theta. Now that we've got the hypotenuse for that smaller triangle, we can use the fact that we have a theta in this triangle to determine that the adjacent side to that particular theta would simply be the hypotenuse times cosine, which is to say cosine times the quantity cosine theta minus sine theta times tangent theta. And if you do that multiplication, you will get cosine squared theta minus sine squared theta, as the cosine will cancel out in the second term. And we also note that this is the same side that we've already determined is equal to cosine of 2 theta. So we've already found our first identity. Cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And this is a good time to note that this particular diagram can be dissected any number of ways using the trigonometric functions, and I encourage you to try that manipulation. In particular, you might want to demonstrate to yourself that cosine squared theta minus sine squared theta is in fact equal to 1 minus 2 sine squared theta, and it's also equal to 2 cosine squared theta minus 1. Part of the fun of trigonometric identities. Continuing on, we can now determine the side lengths of this triangle. So we already know that the hypotenuse is 2 sine theta. So we simply multiply 2 sine theta times cosine to get the adjacent side. And so side 4 ends up being equal to 2 sine theta times cosine theta. And earlier we had determined that side 4 was equivalent to the value of sine of 2 theta. And now we know that that's equal to 2 sine theta cosine theta, so that's our second double angle identity. And then again, going back to the hypotenuse for this triangle, we can determine that 3b would be 2 sine theta times sine theta, which of course would just be 2 sine squared theta. And then since we know that 4 is 2 sine theta cos theta, and 4a is tangent theta, we can subtract one from the other, and determine that 4b would be 2 sine theta cos theta minus tangent theta. And that is then all 13 sides. And so here's the table of the formulas for each of the sides with their side count and side name. Our next step is to apply the theta value given at the beginning of the video, which was 36.8699 degrees, or if you like radians, 0.643501 radians. You then apply that to the formulas given and you get the value column. And I always like reminding myself that usually right triangles don't have hypotenuse equal to 1, so these values need to be scaled based on the actual value of the hypotenuse, which in this case was 5. So we have the column to the right that shows the values of each of the side lengths once they're scaled up by a factor of 5, using theta as given. And because it's always nice to see that in a diagrammatical form, there's the figure with each of the sides labeled based on its length using the given value of theta, where the composite lengths are shown in red. So I hope you had fun dissecting this diagram using the trigonometric functions, and thanks for watching.